How did the first planets form? What forces sculpted them from chaos into order? In the silent vastness of the cosmos, every world carries a story, one that begins in the fiery breath of creation itself. Imagine the universe in its infancy, a swirling chaos of energy and subatomic particles unleashed by the cataclysmic event we now call the Big Bang. Space expanded faster than thought, time began to stretch, and in the fading heat of that unimaginable explosion, the simplest elements, hydrogen and helium, began to take shape. These humble atoms marked the starting line of a journey that would one day lead to stars, planets, oceans, and even life. But in the beginning, there was only darkness. For hundreds of millions of years, the universe remained starless, lightless, and cold, a vast, silent sea known as the Cosmic Dark Ages. And yet, even in that stillness, gravity was at work. Over time, matter began to gather. Invisible hands shaped the first clouds of gas into denser regions, until pressure and heat sparked the universe's first stars into being. These radiant giants, massive, short-lived, and furious, pierced the darkness with nuclear fire. As they lived and died, they sowed the ingredients for everything to come. Their explosive deaths, supernovae, scattered carbon, oxygen, iron, and other heavy elements across the universe. From this stellar debris, cosmic dust began to drift. Fine particles of silicates, metals, and carbon compounds suspended in the vacuum of space. These grains, forged in the hearts of dying stars, would become the building blocks of new worlds. Carried on currents of gravity, they floated in silence, waiting for their time to return to form. The earliest moments of our universe were both violent and precise. In the split second after the Big Bang, space expanded at blistering speeds, an inflationary surge that carried energy across what was once nothing. Matter and antimatter collided and annihilated, leaving behind the fundamental particles that would shape everything we know. As this infant universe cooled, quarks formed protons and neutrons. These joined into the nuclei of hydrogen and helium, the first true atoms. But this was still a silent, starless place. Light existed, but there was nothing yet to shine. True complexity needed more than hydrogen and helium. It needed dust. That dust, microscopic grains born in the final breaths of massive stars, wasn't there in the beginning. It came later, carried by shockwaves from stellar explosions. Silicates, iron, carbon, and ice condensed into fine particles that drifted through space. Over millions of years, they accumulated in cold, quiet regions between the stars, clustering into clouds pregnant with possibility. Cosmic dust may be small, but it is sacred. Without it, planets would never form. Without it, the story of our world would have ended before it began. As dust and gas gathered under gravity's spell, stars began to take shape. These forming stars didn't sit alone in space. They were surrounded by the very materials that created them. Gravity pulled the dust inward, while angular momentum forced it to spin. This spin flattened the material into a swirling disk, an accretion disk, rotating around the newborn star like a halo of raw potential. In these glowing disks, chaos and chemistry converged. Dust grains bumped, stuck, and grew. From tiny specks, they formed pebbles. From pebbles, they became rocks. With time and thousands of collisions, these rocks grew into bodies large enough to feel gravity's grip. Imagine a ballet where each dancer is a particle of stardust, moving in spirals, colliding not with elegance but with power and persistence. The accretion disk was not calm, it was dynamic, violent, alive. But from that turmoil, planets would rise. Within the accretion disks, spinning around young stars, the real work of planetary construction began. As rocky fragments grew in size, their gravity increased, allowing them to pull in more material from the surrounding disk. These growing bodies, called planetesimals, marked the universe's first serious attempts at building worlds. The solar system at this stage was a chaotic arena of growth and destruction. Planetesimals collided, fused, shattered, and sometimes scattered. Each impact changed them. Some became molten, their interiors reshaped by the heat of collision. Others cracked apart, leaving behind debris that would be recycled into new formations. Eventually, some of these planetesimals grew large enough to dominate their region of space. They became proto-planets. Planetary embryos, still far from complete, but destined for greatness. Some remained rocky and small, clinging close to their stars. Others, farther out, gathered gas and ice, growing into the giants that would one day command the outer solar system. But none of them formed in isolation. Their paths were sculpted by competition, by collision, and by time. The early solar system wasn't a tranquil place, it was a battlefield. As protoplanets orbited the sun, their trajectories overlapped and intersected. Gravity tugged them into one another's paths, and where they met, the results were cataclysmic. These weren't small impacts, they were world-shaping events. Collisions could vaporize rock, melt entire crusts, and alter the spin of young planets. One of the most dramatic examples is the likely impact between the proto-Earth and a Mars-sized body known as Theia. This immense collision ejected a cloud of debris into Earth's orbit. Over time, that material coalesced to form our moon, a silent guardian that still watches over our planet today. These collisions weren't accidents, they were part of the process. Through impact after impact, planets gained mass, reshaped their surfaces, and began to form stable orbits. Without this chaotic phase, the solar system would never have achieved its final form. Amid the chaos, another kind of delivery began. Comets and asteroids, rich in water ice and organic molecules, bombarded the inner planets. These icy wanderers came from the fringes of the solar system, places cold enough to preserve volatile compounds. When they struck young planets, they delivered more than just mass. They brought the ingredients for life. On Earth, this cosmic rain seeded the surface with amino acids, simple sugars, and the foundations of biology. More importantly, it delivered water in quantities large enough to flood basins and carve oceans. Earth was uniquely suited to hold on to this water. Its size, gravity, and position in the so-called habitable zone allowed it to keep its atmosphere, resist boiling, and remain wet. Without these deliveries from space, life may never have begun. And without water, Earth would have remained just another silent rock spinning in the dark. Amid all the motion and violence, one force shaped everything: gravity. From the first clumps of dust to the final arrangement of planets, gravity was the sculptor, the judge, and the director of the cosmic performance. It drew matter inward, fused particles into stars, and shaped the orbits of planets. It caused the infall of debris onto growing worlds, pulling more and more mass into their cores. It forced differentiation, where heavier elements sank to the center and lighter materials rose to the surface. Gravity also governed stability. Planets that survived the early chaos did so because gravity found equilibrium, orbits that didn't cross, paths that could endure. It also created interactions that we still witness today. Jupiter's pull shaping the asteroid belt, Earth's gravity holding the moon in place, Saturn's mass guiding the dance of its rings. Without gravity, there would be no structure, only dust drifting endlessly. As some planets developed internal molten cores, spinning masses of iron and nickel, they unlocked one of the most powerful shields in the cosmos, the magnetic field. These invisible barriers stretch far into space, deflecting charged particles from the solar wind and shielding atmospheres from erosion. Earth's magnetic field has been instrumental in preserving not only its air, but its habitability. Without it, our atmosphere would have been slowly stripped away, leaving the surface exposed to deadly radiation. Not every planet was so fortunate. Mars, once possibly wet and warm, lost its magnetic field early. As a result, its atmosphere thinned, its water disappeared, and its surface became barren and frozen. On Venus, a different fate unfolded. A runaway greenhouse effect choked the planet in heat, pressure, and carbon dioxide. Magnetic fields don't just protect, they influence evolution. They determine which planets can retain air, resist radiation, and foster complex chemistry. In the quiet hum beneath our feet, Earth's molten heart beats, an unsung hero of our survival. Eventually, the violence eased. The largest planets had cleared their orbits, either by sweeping up debris or ejecting rivals into the outer reaches of space. The gas and dust that once fed planetary growth dissipated, blown away by stellar winds or pulled into stars. What remained were the survivors, planets with stable orbits and solid identities. In the inner solar system, rocky worlds like Mercury, Venus, Earth, and Mars stood close to the Sun, their surfaces shaped by heat, impact, and geology. Farther out, Jupiter and Saturn reigned with thick atmospheres of hydrogen and helium, surrounded by moons and rings. Beyond them, Uranus and Neptune formed in colder regions, their compositions rich with ices, methane, and hidden storms. Each planet's final form depended on its location, timing, and the materials it gathered. Some worlds cooled quickly, others stayed hot inside, some held atmospheres, others were stripped bare. The result was not uniformity, but diversity, and that diversity became the defining feature of our solar system. Though the earliest elements, hydrogen and helium, formed minutes after the Big Bang, the richness of planetary diversity required something more, the products of stellar alchemy. Within the cores of massive stars, fusion built heavier and heavier atoms: carbon, oxygen, silicon, iron. These elements were scattered by supernovae and incorporated into new star systems, like ours. Each element added new properties to the planets being born. Iron created magnetic cores. Silicon and oxygen combined to form rocky crusts. Carbon laid the foundation for organic chemistry. Sulfur, phosphorus, calcium all contributed to planetary interiors, atmospheres, and eventually life itself. When you look at Earth's surface, or even your own body, you are seeing the periodic table come to life. We are not just made of stardust, we are made of cosmic process. While planets formed, so too did their companions. Some moons were born from violent impacts, like Earth's, ripped from crust and reassembled in orbit. Others were captured, gravitational trophies pulled from passing planetesimals. Still others co-formed alongside their planets, sharing the same disk of dust and gas. But moons are not passive passengers. They influence tides, tilt, and time. Earth's moon, for example, stabilizes our rotation, moderating the seasons and slowing our spin. Without it, Earth's axis might wander chaotically, destabilizing climate and threatening life. Elsewhere, moons like Europa and Enceladus hide oceans beneath icy crusts. Heated by tidal forces, these hidden seas may harbor the conditions for life in places untouched by sunlight. Moons carry memory of impact, migrations, and quiet revolutions. To understand a planet, you must listen to its moons. Not every planet born in a swirling disk survived. In the gravitational chaos of early systems, some young worlds were flung from their orbits, ejected into the cold void between stars. These are the rogue planets, alone, without a sun, drifting through darkness with no day, no night, and no warmth beyond their own fading core. Others failed before they could truly form. They collided too early, broke apart, or simply ran out of material. Their remnants became asteroids, comets, and Kuiper Belt objects, frozen witnesses to the solar system's unfinished stories. Even within our system, we see these echoes. The asteroid belt, once thought to be a failed planet, is now seen as the remains of countless near misses. Pluto, reclassified but never forgotten, reminds us that not all planets fit a tidy definition. For every world that survived, thousands may have vanished. In the great cosmic narrative, silence has a role too. As planets cooled and stabilized, their surfaces began to breathe. Volcanoes released trapped gases, comets brought volatiles from distant reaches, and the interplay of sunlight, chemistry, and gravity forged the first atmospheres. Each planet's breath was different. Venus cloaked itself in carbon dioxide, its surface scorched by a runaway greenhouse effect. Mars may have once held a thicker, warmer atmosphere, but lost it to the solar wind, leaving behind dry riverbeds and a sky gone thin. Earth, by contrast, found balance. Its gravity held onto air, its magnetic field protected it, and its oceans and life began to shape the atmosphere itself. Atmospheres are not just gas, they are memory. They remember every eruption, every comet, every living breath, and sometimes they tell us whether a world could live. On Earth, something extraordinary happened. Amid oceans seeded by comets and warmed by sunlight, molecules began to dance. Simple compounds joined into chains. Chains folded. Some became stable, others self-replicating. This was not life, not yet, but it was close. In deep-sea vents, in tidal pools, in drops of water exposed to lightning and heat, prebiotic chemistry laid the groundwork for biology. The same elements forged in stars, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, began to organize. And somewhere along the line, awareness flickered into existence. Life didn't emerge from outside the cosmic story. It was the next chapter. Today we study not just the planets, but the remnants. Meteorites, ancient fragments that fall to Earth, tell us about the conditions before our planet even formed. Craters on the Moon and Mars preserve histories erased on Earth. Ice cores, rock samples, and spectral data give us insight into how planets evolve, age, and survive. This is cosmic archaeology, reading the language of stone and ice to understand time. We are piecing together a puzzle with fragments from every corner of the solar system and beyond. And each piece tells us something extraordinary. Planets are not accidents, they are inevitable. In recent decades, we've discovered thousands of planets orbiting distant stars. Some are scorched giants hugging their suns. Some drift in eternal twilight around dim red dwarfs. Some lie in the habitable zone, not too hot, not too cold, where water might flow and chemistry might flourish. Each discovery reminds us that our solar system is not alone in its creativity. Planet formation is not rare, it is cosmic standard. And if planets are common, perhaps life is too. Perhaps out there, another world spins beneath a pale sky, wondering if it's alone. From the fire of the Big Bang to the quiet breath of life, this is how planets are formed. A story written in stardust and gravity, told through collisions, orbits, and time itself. We've seen how the first atoms gathered into stars, how those stars lived and died, scattering dust across the cosmos, how that dust spun into disks, collided, grew, and became something more. Now, we understand how the first planets were created, step by step, layer by layer, through forces both violent and delicate. We've followed the journey from cosmic dust to the architecture of entire worlds. But this isn't just a story of planets, it's our story. Because everything we are, our oceans, our bones, our breath, was born from the same processes that built the stars. To ask how planets form is to ask where we came from. And if you found this journey through the dark intriguing, like this video and subscribe for more content about the mysteries of our universe. Together, let's keep asking the big questions and reaching for the stars.